Hello everyone. Let's review the first set of topics covered in the rotational motion unit, which includes rotational kinematics, rotational inertia or moment of inertia, and rotational kinetic energy. Rotational kinematics includes angular position, angular displacement, angular velocity, and angular acceleration. Let's take a closer look at each of these quantities. Angular position is a reference point from which the angle theta will increase or decrease and is taken at a certain arc length and radius from an axis looking down on the rotation in the plane perpendicular to the rotation axis. Here we are looking at a turntable that can rotate about an axis perpendicular to the tabletop. We will call the plane of the table the XY plane, and the axis of rotation will be the z-axis. The arc length is a distance s counterclockwise from the x-axis, and r is the radius from the rotation axis. This allows us to define a starting reference point for theta. Most often, though, we will simply call theta naught 0 and start the problem from that point with theta naught starting at the x-axis. Angular displacement, delta theta, is a change in angular position and defined as theta final minus theta initial. This is the angle through which the rotation occurs. Since an object can rotate in two directions around an axis, the delta theta is defined as positive for a counterclockwise rotation when viewed from above as we are viewing this rotation. It is considered negative in a clockwise rotation as viewed from above as we are seeing it now. Again, that is positive change in theta in the counterclockwise direction. Although we can give angular displacement a positive or negative value, it is not a vector quantity because it fails the commutative property of vector addition. Average angular velocity is the rate change of angular displacement, or delta theta divided by delta t. The instantaneous angular velocity can be determined by the time derivative of theta, or d theta divided by dt. Again, we describe a positive angular velocity as a counterclockwise rotation. And we describe a negative angular velocity as a clockwise rotation. Again, that's positive angular velocity as a counterclockwise rotation. However, angular velocity is a vector quantity, and it does have a direction associated with it. The direction of angular velocity is actually perpendicular to the plane in which delta theta is occurring. And we use the right-hand rule to aid us in determining the direction. Our right fingers wrap around the rotation axis in the direction of rotation, and our right thumb points in the direction of angular velocity along the rotation axis. Again, our right fingers wrap around the rotation axis in the direction of rotation, and our right thumb points along the axis in the direction of angular velocity. Average angular acceleration is the rate change of angular velocity, or delta omega divided by delta t. The instantaneous angular acceleration can be determined by the time derivative of angular velocity, or d omega divided by dt. A positive acceleration, angular acceleration, is an increase in the angular velocity in the positive direction. It is also a decrease in the angular velocity in the negative direction. A negative angular acceleration is an increase in angular velocity in the negative direction. It is also a decrease in speed in the positive direction as shown here. Just as with angular velocity, the direction of angular acceleration is a vector along the rotation axis, and it's also determined by the right-hand rule. Each object has a tendency to resist a change in its state of rotational motion. It has rotational inertia. If it is already rotating, it wants to keep on rotating, like this rotational inertia demonstrator. If it is at rest, it wants to stay at rest, like these objects right here. The quantity that describes an object's rotational inertia is its moment of inertia given the symbol I. In general, I is found by summing up all the mr squared values for each of the particles in that object, which basically describes how much and where the mass is located in relation to the rotation axis, which is different for each object. So it'll be different for this disk, this hoop, or these masses at the end of the rotational demonstrator. Let's take a closer look at the rotational inertia demonstrator. Here we've got a mass at the end of the string. That string is wrapped around the pulley on the rotational inertia demonstrator at a certain distance from the rotation axis, a certain radius away. This mass is going to apply a force in that downward direction, causing this to spin. Right now we've got most of the mass concentrated close to the rotation axis. When I let this go, it's going to pick up speed rather quickly because it has such a low moment of inertia. If we wrap this back up and I move that mass toward the ends of the rods, so now the mass is far away from the rotation axis, this increases the moment of inertia, and we should expect it to spin a lot slower. So with a large moment of inertia, it does not want to get moving very quickly. So here we let it go, and we see, yes indeed, it's moving pretty slowly. So it does not have a large rotational speed or rotational velocity or angular velocity. So the further the masses are out, the more moment of inertia, the more rotational inertia. The closer those masses are toward the rotation axis, the lower the rotational inertia. Just like the translational counterpart of kinetic energy, which is 1/2 mv squared, the rotational kinetic energy depends on the rotational equivalent of mass and the square of the velocity, namely the moment of inertia and the square of the angular velocity. Since objects can possess motion by rotating about an axis without translating through space, we need to be able to describe this energy of motion. Another form of rotational energy is torsional spring potential energy. Torsion springs cause a twisting motion, like the one I have here that's connected to a torsion bar. We can also have wound springs, such as those in wind-up watches, and we also have helically wound springs like those in mouse traps. The spring potential for rotational motion, or the torsion spring potential energy, is very similar to the linear spring potential energy. Linear spring potential is 1/2 kx squared for the rotational counterpart. we've got 1/2 kappa theta squared, where kappa is the spring potential, that torsion spring potential, and that's going to be different for each spring. Here I've got a thick piece of wood, and it'll give us a certain twisting or oscillation there, and I could use other pieces of wood like this, or pieces of metal, any material that we can twist, and it will want to restore itself, twist back. So we've got different kappas, and that's based on each one of the, or each individual spring. Theta then is the that angular displacement, so I can twist it so far, and it wants to restore, it wants to go back to its original position. And you see it's oscillating back and forth, just like that. Well, I hope this podcast has helped you to review these principles in this chapter. You can view it as many times as you like, and as always, feel free to ask questions at school about anything. Good luck on the quiz and the test.